Picture this. You've torn down over 20 battery packs. You know the process cold. But this one stops you dead. 40 hours in a freezer, 8 hours of grinding, cutting, hammering, and when it's finally open, what's inside changes the conversation around EVs entirely. This is BYD's second-generation Blade battery, the most advanced LFP pack on the planet. And it just revealed an uncomfortable truth the industry isn't ready to talk about. BYD's second-generation Blade battery isn't just another lithium iron phosphate pack. It's a fundamentally different way of thinking about what a battery can be. Most battery packs follow a predictable formula. Cells go into modules. Modules go into a pack. Pack goes into the car. Simple, proven. And by most modern standards, increasingly outdated. BYD threw that formula away. In the Blade system, there are no modules. The cells themselves, long, flat, blade-shaped, are arranged so precisely that they become the structural skeleton of the pack. They don't just store energy, they hold the car together. The result is a pack weighing around 572 kilograms, housing 170 cells connected in series, capable of megawatt-level charging. That means 1,000 kilowatts. To put that in perspective, most fast chargers today deliver somewhere between 50 and 350 kilowatts. BYD's second-gen Blade is engineered to handle 3 times the top end of what most infrastructure can currently provide. It also uses a refrigerant-based direct cooling system, not traditional liquid coolant. Refrigerant changes phase as it absorbs heat, pulling thermal energy away from the cells far more efficiently. That's a meaningful engineering distinction. It's why this pack can sustain ultra-fast charging, without the thermal runaway risks that have haunted earlier EV battery designs. Peak temperature during ultra-fast charging, around 71 degrees Celsius. That number used to be considered dangerous. With the Blade's cell chemistry and cooling architecture, it isn't on paper. This is world-class engineering. The Teardown team knew that going in. What they didn't know was how hard the battery would fight back. The Teardown was streamed live on Weibo, China's major social media platform, by a team that had previously dismantled more than 20 different battery packs from manufacturers around the world. These weren't amateurs. These were engineers with methodology, tools, and experience. And still, this pack nearly beat them. The first obstacle was the structural adhesive. BYD uses bonding compound throughout. Around the bus bars, the battery tab connections, the signal wiring, the internal frame. This isn't incidental. The adhesive is load-bearing. It's part of what gives the Blade its extraordinary rigidity and crash resistance. Remove it carelessly, and the pack's structural integrity collapses, which is precisely the problem. Under normal circumstances, you'd use heat or chemical solvents to break adhesive bonds. Neither option is viable near live battery cells. Heat risks thermal runaway. Chemicals risk cell degradation or worse. So the team tried cold instead. They froze the entire pack in cold storage for 40 consecutive hours, hoping the thermal contraction would make the adhesive brittle enough to crack cleanly. It helped, but only barely. Even after the freeze, it still took 8 hours of controlled destructive disassembly, grinding, cutting, and carefully applied mechanical force to actually access the internal structure. What they found inside was genuinely impressive. A ladder-shaped reinforcement frame divided the pack into distinct sections. High-voltage compartments were positioned at the front and rear. The battery management system was integrated directly into the pack architecture to reduce wiring complexity and overall component count. Energy density at the pack level came in at approximately 132 watt-hours per kilogram. At the cell level, 180 watt-hours per kilogram, slightly below BYD's own stated figure of 192, but not dramatically so. More notably, pack integration efficiency reached 73.6 PHN/TRM. That number reflects how much of the cell-level energy density survives the engineering process of assembling a full pack. 73.6 PHN/TRM is high. Genuinely high. The engineering story here is almost entirely positive. Then the team asked a different question. And that's where the conversation got uncomfortable. Before getting to the difficult question, it's worth understanding just how safe this battery actually is. During the teardown, the team subjected the blade pack to an 8mm nail penetration test. One of the most aggressive standard tests in battery safety evaluation. A hardened nail is driven directly into the cell. In many chemistries, this triggers immediate thermal runaway. Fire, explosion, catastrophic failure. The blade pack passed without incident. No fire, no smoke, no explosion. They also ground the external casing, hammered the structure, and pushed the pack through conditions that would have destroyed most competitors' products. The pack held. This is not accidental. Lithium iron phosphate chemistry is inherently more thermally stable than nickel-manganese cobalt alternatives. Combined with BYD's refrigerant cooling and the structural integration of the cells, the result is a battery that is arguably the safest high-performance pack currently available in a production EV, and simultaneously the fastest charging LFP battery on the market today. That is a remarkable combination. But here is the engineering trade-off that the industry rarely talks about openly. The same structural adhesive that makes this pack strong, safe, and crash-resistant also makes it nearly impossible to repair at the component level. The same cell-to-pack integration that improves energy density and reduces weight also means that accessing individual cells requires essentially destroying the pack in the process. If a single cell group fails outside of warranty, if a collision damages one section of the pack, an independent repair shop would face an 8-hour destructive teardown just to assess the damage. Replacing individual cells isn't realistically viable. The likely outcome in most damage scenarios is full pack replacement. This is not a BYD-specific problem. Tesla's 4680 structural battery pack, which famously uses expanding foam to fill structural voids, presents nearly identical serviceability challenges. Monroe Live's teardown of that pack drew the same conclusions years ago. The industry is converging on highly integrated battery architecture, and the repairability question is converging with it. The teardown team drew a direct parallel between the Blade and the 4680, and the comparison is fair. Both packs prioritize structural integration over serviceability. Both use aggressive bonding techniques that simplify assembly at scale but complicate repair. Both represent a deliberate engineering philosophy, optimize for performance, safety, and manufacturing efficiency. And except that end-of-life handling becomes more complex as a consequence. The downstream effects of this philosophy are already visible. Insurance premiums on structurally integrated EVs are trending higher than on vehicles with traditional modular battery designs. Repair costs after moderate collisions are elevated, and battery recycling, while technically possible, becomes significantly more expensive when packs cannot be cleanly disassembled at the cell level. There is also a legal dimension worth noting. In the days following this particular teardown, a Chinese court ordered a separate automotive blogger to pay the equivalent of $293,000 in compensation to BYD over unverified claims made online. The legal environment around EV criticism in China is tightening. That context matters, not because it invalidates the teardown findings, but because it illustrates how politically charged technical criticism has become in this market. The teardown team faced accusations from brand loyalists, claiming deliberate damage or manipulated testing. The team responded directly. The cooling plate remained intact throughout, and a heater used earlier in the process was for standard pre-test discharge, not for thermal manipulation. This is textbook teardown methodology. The repairability concern is not a criticism of BYD's engineering. It is a legitimate consequence of choices that the entire industry is making simultaneously, and it deserves an honest conversation. BYD's second-generation Blade battery is by almost every technical measure an extraordinary achievement. It charges faster than anything else currently available in a production EV. It passes safety tests that destroy competing chemistries. It integrates energy storage and vehicle structure in ways that were considered impractical a decade ago, and it takes 40 hours of freezing and 8 hours of grinding just to open. That is not a flaw in isolation. It is the cost of the engineering decisions that make everything else possible. The automotive industry is learning slowly, publicly, that optimization in one direction always creates pressure somewhere else. Safer, faster, lighter, more integrated, harder to fix, more expensive to insure, more complex to recycle. The Blade battery is the clearest example yet of where EV technology is heading. The question isn't whether this architecture will dominate the next decade. The question is whether the infrastructure around it, insurance, repair, recycling, can keep up.